everyone. Today we're going to look at section 7.4 and look at some of the qualitative changes that can occur in equilibrium systems. So analogy to consider is if you've ever tried walking up an escalator that is going down. If you walk up at the same rate that the escalator is going down, what will happen? You will stay in the same spot. This is like a dynamic equilibrium. If the escalator suddenly speeds up and you do not, what will happen? You will be shifted down. This is like a disturbance in a dynamic equilibrium. To reestablish the equilibrium, what are you going to have to do? To compensate for it, you're going to need to speed up. This is what mimics what occurs in chemical equilibrium during reactions. So what are some things that can disturb a chemical equilibrium? Changes in pressure, temperature, concentration, and volume, or a combination of these, can cause a disturbance in a chemical equilibrium. These changes can be explained by Le Chatelier's principle. He was a French chemist who studied chemical reactions at equilibrium, and he always started with a well-defined initial equilibrium state. Once he achieved that, he would then change one of the properties of the systems, and then he observed what would temporarily happen in this non-equilibrium state until a new equilibrium state would be established. So he performed this experiment over many reactions and observed always the same results. And the reason why he was doing these experiments is he wanted to maximize the yield of products from chemical systems. And he saw a pattern as he was gathering his evidence. So what Le Chatelier saw is that when a chemical system at equilibrium is disturbed by a change in a property, the system will adjust in a way that opposes that change. All right, so let's take a look at what he means. So this is basically the important explanation or pattern that is what is Le Chatelier's principle. So based on these patterns that he saw, it allows chemists to predict the qualitative effects of changes that occur either by concentration, pressure, and temperature on a chemical reaction during a system that is at equilibrium. So let's take a look at some of these factors that change or are disturbances to a chemical equilibrium and how they apply using Le Chatelier's principle. So the first one would be concentration. Very simple one to understand. If the equilibrium system is subjected to a change or a stress, the process occurs that tend to partially counteract that imposed change. That is Le Chatelier's principle. So when we adjusted the system that's at equilibrium, the change in the concentrations of the reactants or products, when they move, is going to be called an equilibrium shift. So let us consider this general reaction here of A plus B as our reactants and C and D as our products. This system is at equilibrium. Now, if I were to inject this reaction vessel with some more product or reactants of A or B, it doesn't matter which one, if I add more of it to the system which is already at equilibrium, the equilibrium is going to move to the right. Why? Because it wishes to consume that extra added product, use it up. Now, likewise, if I were to remove either reactant A or B from the reaction vessel, the equilibrium would shift to the left. Why? Because it wants to make more of those reactants. All right, so it does it in the opposite direction to the imposed change. On the other hand, we can also cause stresses by the products. So if I increase either product, C or D, the equilibrium will also shift to the left because we want to consume this added product. All right, so it's going to go to the left until a new equilibrium is achieved. And finally, the last possibility is we could decrease the concentration of both the reactant and the product, the two products, C or D. And if we decrease them, the equilibrium is going to shift to the right because we want to make more of that product. All right, so pretty straightforward. So in general case, we can say that any reactant or product which is already at equilibrium, the reaction will occur to partially use up the added product or reactant. If the reactant or product is removed, then the reaction will occur that produces more of that removed reactant or product. All right, so what's important to note that our equilibrium constant, K, does not change. All right, so that's the easiest to understand of what a stress that can potentially happen in an equilibrium to cause an equilibrium shift. Let's pay attention to and look at the next one is temperature. So equilibriums can also be disturbed by the addition or the removal of energy. Okay, that is thermal energy. So if we apply Le Chatelier's principle, we can think of energy as either a reactant or a product. So we need to determine which direction is the endothermic and which one is the exothermic reaction. So when energy is absorbed, it's an endothermic reaction, if you recall from our last unit. So we would write it as part of the products. Okay, so reactants plus the energy produces my products. If the energy is released, then it is an exothermic reaction. So we would add the word energy to the product side of the equilibrium equation. All right, so that is important to realize when we are thinking about temperature as a stress. So let's consider this general equilibrium equation. All right, so if we have A plus B plus my energy, I see that my energy term is on the left-hand side as part of the reactants. So that means that the forward reaction is endothermic. So I'll write that over the top of the forward arrow, that it is endothermic. Okay, that's the forward reaction. That is what I have deduced based on the thermochemical equation here. All right, so that's in the forward direction. Thus, the opposite direction, the reverse reaction, is going to be therefore exothermic. Okay, so that is my reverse reaction. So that's the important thing that you've got to first come up with. So remembering that when we have an endothermic reaction, it really means that our system is getting colder, while an exothermic reaction is getting hotter. So let's consider what the possible stresses could be to this equilibrium. If the equilibrium has a rise in the temperature, which means the temperature goes up, hence it's going to get hotter, which way will the equilibrium go in order to absorb that extra added heat? All right, so you want to go in the counter stress. All right, so if it's getting hotter, we want it to cool it off. So the direction in which it gets colder is the endothermic direction. So that's why we move to the right to absorb that added heat. And if the temperature decreases, that means it's getting colder, we want to generate heat. So the equilibrium in this particular reaction will shift to the left, because in the left, going to the left, is the exothermic reaction. All right, so then we would move to the left to generate heat. So generally speaking then, if the temperature of the system at equilibrium is raised by adding thermal energy, then the net reaction will want to absorb it. And if the temperature at equilibrium is lowered by thermal energy, by removing that thermal energy, then the net reaction will take place that will liberate that energy. And once again, the value of our equilibrium constant, K, in this case, is going to change. All right, it is going to change because temperature is changing. We're not at a constant temperature. All right, so in summary then, if energy is either added or removed for a chemical reaction system at equilibrium, the equilibrium will shift in the direction that it will compensate for that change in energy. Okay, so pretty straightforward. Now, looking at the final two stresses that can take place on an equilibrium, and those are pressure and volume. These are for gaseous systems only. All right, so if you've ever pumped up a tire, you will know that changing the volume of a sealed container of the gas also changes the pressure. This is Boyle's law, which in turn changes the concentration of the gases in the container. So we are going to assume that the gases behave as an ideal gas. Okay, and if you recall from grade 11, a hypothetical gas which is composed of entities without any size, they're going to travel in straight lines and have no attraction to each other. Hence, there's no intermolecular forces. And it's going to obey all the gas laws, Charles' law, Boyle's law, and Gay-Lussac's law. So these laws you learned in grade 11. And so if Boyle's law holds true for a pure gas or for mixtures of a gas, okay? And don't forget that in a mixture, each gas is going to exert its own partial pressure, which we recall as well from grade 11 as Dalton's law of partial pressures. So let's take a look at an example here. So here we have an equilibrium which is established between nitrogen and hydrogen, forming ammonia. And since it's a sealed container, we have established an equilibrium. All right, so you've got both the synthesis of ammonia as well as the decomposition of ammonia taking place. So this first diagram here is at equilibrium. This one is at equilibrium. But then I apply a pressure, which is my red line here. I've decreased my volume by half. And when I decrease the volume by half, now all the molecules have less space. So they have to compensate by the removal of that space, by making the molecules take up less space. So if we look at this equation here, we see that on the left-hand side of the equation, I have 4 molecules. And on the right side of the equation, I have 2 molecules. 4 molecules take up more space than 3 molecules, or 2 molecules rather. So when we apply the stress of decreasing the volume or increasing the pressure, the counter reaction to that stress would be to create molecules that are less, that we have less molecules present. So when this type of stress happens, this reaction will move towards the products, all right, or towards the right. All right, so this is sort of all explained here in words. Okay, so once again, if we reduce the volume by a half, our total pressure is going to double. Because the partial pressures of the gas will double, the number of molecules of each gas per unit volume will also double. So according to this balanced equation, we got 4 reactants and we have 2 product entities. So the total partial pressure of the reactants is twice that of the products, so therefore the volume is going to be decreased and the change in concentration of reactants is greater than the products. So our equilibrium then will have to shift to the right to reduce the total number of entities per unit volume from 4 to 2, which will reduce the overall pressure of the system. So in summary, when we change pressure or volume, when volume decreases or pressure increases, the equilibrium will shift in the direction where there is the least number of molecules, and vice versa. All right? If we increase the volume and decrease the pressure, it will shift in the direction where we have the greatest number of molecules. All right? And so these are important with respect to pressure and volume. Now, another important thing to note here is that the addition of a catalyst or a noble gas does not have an effect on the equilibrium. All right, so let's take a look at some examples of how we can go about and see if we are able to understand these concepts of Le Chatelier's principle and how they apply using a specific reaction. So let's take a look at this example here. So we've got sulfur dioxide plus oxygen forming sulfur trioxide plus energy. All right, so right away I recognize that the forward reaction is, because my energy term is on the left, on the product side, I know that the forward reaction is exothermic, thus making the reverse reaction endothermic. All right, so let's take a look at what's happening here. First possible stress would be to increase the concentration of SO2. So if I increase the concentration of one of the reactants, the equilibrium is going to shift to the right because it wants to use it up. All right. The excess reactants. Now, pressure on the system is decreased. I always like to think of pressure with respect to volume. So if pressure decreases, that means that volume increases. So I've got more space. That's the way I'm going to think about it. Okay, so then I look to see how many molecules are involved in this reaction. So on the reactant side, I have 2 plus 1, so I've got 3 molecules on the left. And on my product side, I see that I only have 2 molecules. So if I increase the volume, I want to offset the stress, so I want to move in the direction that is going to have more space. So I'm going to shift to the left. Okay, so we have more molecules. Okay, to take up more space. Right, looking at the next stress, which would be temperature. All right, if I add temperature, if I increase the temperature, it's getting hotter, so I want to counter that stress. So I want it to cool the system. So the direction in which it gets colder is once again moving to the left. because that is the endothermic reaction. All right, so to offset the increase in temperature, we're going to move in the endothermic direction. Now, if the volume of the container is increased, once again, I've got more space for more molecules. So this stress again would cause the equilibrium to shift to the left. Okay, so we have more space available. So more molecules are required. Now, if we add a catalyst to this particular reaction, we know that it doesn't have no effect. It's not going to cause a stress to the overall equilibrium. Likewise, by adding this inert gas of helium, it too will have no effect. Okay, no effect on the equilibrium. All right, so that's a typical type question where you have to be able to analyze the stresses and identify in which direction, using Le Chatelier's principle, which direction it will move in order to counteract that stress. So folks, your homework then is to read these sections 7.3 and 7.4. Try the homework questions, and a good idea through your reading is to summarize some of the applications of Le Chatelier's principles found in your reading in section 7.4. And there are 3 of them. So good luck, and we'll see you in the next lesson.